Hi, I'm Ryan Lembitz, and this is my senior project on iPhone LCD remanufacturing. Our story starts with a more than common occurrence in the 21st century. You're walking along when suddenly you just lose grip of your phone. You go to pick it up, and unfortunately, the screen is totally destroyed. The typical repair process looks something like this. The damaged glass with working LCD and digitizer are removed from the iPhone. Then, all small parts are removed from the damaged glass with working LCD and digitizer. A new panel is tested, and then all small parts are reinstalled back onto the working LCD digitizer with uncracked glass. Then this assembly is reinstalled back onto the unibody of the iPhone. The repair results in a great-looking iPhone screen free of any defects or cracks. However, as a byproduct of the repair process, we're still left with a good LCD and digitizer with cracked glass. The problem in this repair process arises from the byproduct. Repairing iPhone screens on a mass scale, we are left with hundreds of working LCDs and digitizers, yet they are rendered useless because of their cracked glass. We saved our stock of broken iPhone screens for 1 month, and this is what we got. In order to successfully solve this problem and reduce the waste and environmental impact caused by the screen replacement process, it is essential to remanufacture the iPhone screen by first reclaiming the working LCD and digitizer and then installing the working LCD and digitizer onto new glass. This will reduce overall cost so long as OEM durability specifications are met by the remanufactured screen. Here we see the overall process flow followed by LCDs as they undergo the LCD remanufacturing process. Much time and effort has been spent on finalizing this process flow in terms of determining which machines and consumables would be necessary for its success. As seen from the main chronological processes on the left, most screens follow the path of glass removal, polarizer removal, OCA cleaning, polarizer lamination, glass lamination, and then bubble removal. Each one of these processes will be viewed more in depth in order to confirm yield rates and cycle times per process, which were used to calculate the overall feasibility of the remanufacturing process. Now this is great to see on paper, but let's go ahead and see it in action before we jump into its analysis. First, the incoming part is tested. Then, the frame is punctured to allow removal and the cracked glass is taped. Then, the frame is removed and the glass is then removed from the working LCD and digitizer. The LCD is tested again, and then it is input into polarizer removal. Once the polarizer is removed, the screen looks like this. However, with a polarizer on it, it looks like this. You can actually see the LCD. Large amounts of OCA are removed by a razor blade, while smudges are removed with mass airflow sensor cleaner, which contains a high amount of N-hexane, which is a good solvent. The LCD is tested again before polarizer lamination. 2 vacuum plates hold both the LCD and the polarizer steady, and then an automated process laminates the polarizer to the LCD. The glass can now be laminated onto the working LCD and digitizer. And then, once lamination is initiated, it is put into the vacuum OCA lamination machine. Bubbles are removed in the autoclave, and then the final product is tested, with the damaged glass and polarizer shown on the right. It can be noted from this process flow that modifications to the original process flow had to be made as the process began to be followed, one of which was bypassing polarizer removal and lamination and simply cleaning the OCA from the polarizer film. This is only possible if the film remained intact after glass removal. This shows a considerable benefit in terms of reduced cycle time and consumable costs and will be investigated later in this video. Additionally, it was found that another deviation had to be made from the main process flow as the bubble removal process showed very low initial yield rates without rework. Summary of this will follow in this video, yet a more in-depth analysis can be found in the written report. Beginning with the first process in the chronological process flow, glass removal yield rates and cycle times were investigated for a single batch of iPhone 6 and iPhone 6s LCDs. It was found that the overall yield rate of this process was 93%. However, incoming screens which showed a high crack severity of 3 illustrated only a 74% yield rate. This was expected as screens with more severely damaged glass had a tendency of having pieces of this cracked glass becoming dislodged from the adhesive and puncturing the LCD or digitizer with the passing of the molybdenum wire. To decrease the fallout rate from cracked screens with a severity of 3, higher grade adhesive was used to hold the broken glass. Additionally, a new application method of rolling on the adhesive with a silicone roller was introduced. Benefits for these can be found in the written report. It was known that the polarizer on the LCD must be removed if and only if it was damaged during the glass removal. As the glass removal technique became more controlled and calculated, it was found that some LCDs would exit the glass removal process with their polarizer film still intact. A yield study was conducted to discover just how many LCDs could be used with their original polarizer film, and it was found from the results that 40% of incoming LCDs still had their polarizers intact, as shown by the contingency plot on the left. This allowed the LCDs to follow an alternative process flow as illustrated on the right, where the LCD would simply undergo OCA cleaning process and forego the polarizer removal and polarizer lamination processes. This allowed a cycle time reduction of around 2 minutes to be achieved from the alternative process flow, as well as save the consumable cost of the polarizer film. Not to mention, this also saved the LCD from the fallout associated with the LCD removal and lamination processes. If the polarizer is damaged during glass removal, the polarizer would have to be removed in order to allow replacement further down the line. An overall yield rate of 91.75% was found for all LCDs. As seen in the variability chart on the left, cycle times for this process were found to be relatively low, as there is little to no prep time for this process. The highest driving force for cycle time of this process is the blade takes about 5 minutes to fully heat and must be left for a minute to reheat after each removal. This is not a great issue, and this process can be easily operated in tandem with glass removal by one operator. However, a higher wattage inductive heater must be invested in if the process capability is to be maxed. As there is a layer of OCA above and also below the polarizer, it was found that all non-defective screens must undergo OCA cleaning whether or not the polarizer is damaged during glass removal or not. A higher fallout rate was seen for LCDs with a greater surface area as they required more time and effort to be clean. However, the overall yield rate of the process was found to be 91.56% with a very high cycle time of around 245 seconds. The yield rate is considered controlled for this process as it is a manual process which is inherently susceptible to human error, and therefore any yield rate above 90% is fairly good. However, the cycle time for this process is extremely high and must be reduced at a later date in order to allow full process optimization with a single cleaning station. Polarizer lamination showed the highest success rate of all processes, as there are no sharp objects or direct stress concentrations associated with the lamination of a polarizer. As such, only a single LCD was lost due to operator error, and therefore the yield of this process will not need to be investigated if the process is to be scaled. The cycle time for this process is associated with ensuring the LCD has a perfect mirror-like finish as well as aligning the polarizer film to the LCD. Investigation will be performed to cycle time reduction if the process is to be scaled. All LCDs with original and reapplied polarizers are now joined back to the same overall process flow for glass lamination. This process has an overall yield of 97.88% with all failures coming from human error due to loading the jig or the lamination machine, which results in either a cracked LCD or damaged flex connector from being pinched. This yield rate can be increased slightly with regular service intervals for cleaning the alignment jig. However, this is a fairly stable yield and will not be a main concern when scaling. This process also illustrates a very stable cycle time as it is a fully automated process, and therefore the only variation in cycle time will arise from alignment within the jig as well as possibly loading and unloading the part from the automated machine. Initial bubble removal yield rates were very low at a first pass yield rate of around 66%. It was found that larger screens had a much larger chance of developing failures due to bubbles versus their smaller screen counterparts. This is due to bubbles having to travel further within the OCA to reach the edges of the screen to be released. From the initial first pass yield rate, it was apparent something had to be done to increase this yield. Although focusing on the upstream processes has potential, this will be focused on more during scaling of the project. To fix the issue immediately and to qualify the process, a rework procedure was developed. The screens were placed on a hot plate for 2 minutes to soften the OCA, and then delaminated, reheat, and then input into bubble removal. Repeating this process showed yield rates of 88% and 96% respective to primary and secondary rework procedures. This is acceptable and allows the capability of the process to be analyzed. Cycle time for multiple rework procedures is not a necessary concern, as multiple parts can be input at once into the autoclave, and also bubble removal is a fully automated process in the autoclave. Once yield rates and cycle times had been analyzed and qualified for each process, the process was able to undergo an accumulated cost analysis. What we found from the accumulated cost analysis is that there's a savings or potential profit of $21.70 for every iPhone 6 that is remanufactured, and for every iPhone 6s there's a savings or potential profit of $30.61. The accumulated cost model was calculated using the yields and cycle times for each process throughout the entire process flow. Additionally, the purchase price for the raw material was calculated from the scrap costs of cracked LCDs given by third-party companies, a labor rate of $15 an hour, indirect costs of $1,000 a month, and direct labor hours of $12,000 a month. From this accumulated cost model, it is very apparent that this process is extremely profitable. If 25 screens were remanufactured per day using a 5-day work week at 52 weeks in a year, this process would bring in an average of $165,000 per year. Therefore, this process will be pursued further for Polytronics.